What's relative humidity defined as?
Relative humidity is the amount of water vapor in the air over the amount of water vapor that can be in the air, which is W of S, sub S.
Okay, and what's W stand for?
The exact amount of vapor in the air.
Okay. Do you understand when I say it's the exact amount of water vapor in the air? It's sort of like saying, I mean, you wouldn't ask the question, how many people are there, right? If I said that to you and I said, give me the answer, how many people are there? What would you say to me?
You give like an approximation, like there's some or there's a few people there.
Well, no. I mean, how many people are there? Well, you'd have to ask me a question before you could answer that. What would you have to ask me?
You? H.
Okay, answer the question. How many people are there? Zach?
D.
I don't. You would have to count the people.
O. Two.
What?
U.
How many people are there? Just give me the answer.
Some people.
No.
No. How many people? Ryan?
Like where?
Well, isn't that the question you have to ask first? How many people are there where? At COD, in Illinois, in DuPage County, in the world, in the United States, in Mexico? I mean, don't you have to answer that question? So if I said, how much water vapor is there? What do you think the answer is? I mean, wouldn't you have to say, where? Do you agree that water vapor content is going to be different everywhere that you go? So you can't just say how much there is. You have to tell me, well, how much is there here? And how big is here? You put it in a box that's a cubic, that's a kilogram. So you're going to take a kilogram, and then you want to say, well, how much water vapor is in that kilogram of air? So you're giving it a location, but it's the exact amount. Now, do you agree in the discussion that I gave you is that if I have a sample of air and I said, well, how much water vapor is in there? You'd say, well, it's W. And what's the unit of W?
Grams per kilogram.
Right, so you're saying you take out all the water vapor and you weigh it, and that would be so many grams. And then what are you left with?
Dry air.
You're left with just dry air, and that's the kilograms of dry air. You weigh that. But if I asked you, how do you change the amount of water vapor in the air, what would you have to say?
Condensation.
Make it easier, Isaac. How do you change the amount of water vapor that's in there?
There needs to be liquid.
No. If you had a bunch of marbles in a jar and I said, how many marbles are in that jar? You'd say, well, I'll count them, right? And I said, well, how do you change the number of marbles?
You
What's
weigh
the answer? Huh?
Weigh it.
Well, I mean, you could, but I'm saying, how do you change the number of marbles in the jar?
Take some or remove some.
Right? I mean, well, you said the same thing twice.
I did.
Well, what are the two ways?
Take some or remove some.
If you take some, aren't you removing it?
Oh yeah. It's true.
Put some in or take it out.
Yeah.
So how do you change the amount of water vapor in the air? Put some in or take some out, right? That's the answer. How do you change the amount of water vapor molecules that's in the air? You take some out, you put some in. Now, what do you call the process of taking vapor out of the air? Sam?
Evaporation. No, condensation.
You sure?
take vapor out of the air, turning it into
Yeah, so you go from liquid to vapor. And how do you put vapor into the air?
by evaporation.
Okay. Now, in order to have evaporation or condensation taking place, you guys remember the other day I told you about present imperfect tense? That means you're talking about it happening now. So I'm asking you, how do you know if you have condensation or evaporation taking place, happening now? What do you need? What do you need present?
Bless you.
Thank you.
Don't you need water vapor and liquid water for the process to happen?
Right? You need both, right? Because if you had no liquid, is evaporation or condensation taking place? There's nothing to evaporate, or you're not putting any back into it. So in order to have evaporation or condensation currently taking place right now, you need to have both liquid and vapor. Now, what's the first fact about vapor that you all need to know?
It's invisible.
Okay, it's invisible. So do you have water vapor in the air? So imagine that you have a box. Do you have water vapor in the air? How do you know?
There's always some
Exactly, and how much do you have?
W.
You have W, okay? How do you know if you have liquid in the box?
You can see it.
And what does it look like? What does liquid in a box of air look like?
Cloud.
Cloud.
Okay, so I don't want you thinking that there's like a pond of water, which there could be, but you have to consider that there is clouds. Clouds are condensed water vapor. So there's little droplets of water. So that's what it looks like when there is liquid water. Okay, so I take a box of air and I lift the box up. First thing that happens to it.
Pressure outside the box decreases.
Second,
Pressure inside decreases.
because
It always has to be equal.
next thing that happens to it. Aaron,
The box expands.
the box expands. And what else happens to it?
Cools.
What rate?
10 degrees Celsius per kilometer.
It's called.
Adiabatic lapse rate.
Put a word before it. Which adiabatic lapse rate?
Dry.
Okay. Now, when I lift that box, what happens to W? What happens to W? So everybody goes up, goes down, stays the same. Give me the answer. So everybody has to do it. I see one. I see Tom. I see Aaron. Aaron, are you giving me this one? What are the rest of you guys doing?
Not too sure.
Tim and Lena are saying it goes up. Ryan?
Goes up.
That's 3 ups, 2 stays the same. Zach, what do you, and then I don't know. Zach,
I wasn't here for a few seconds. Could you repeat the question?
you said up, okay. And Isaac,
I'm sorry. Can you repeat the question again?
what happens to W when I lift the box adiabatically?
It goes up.
Why? Tim, explain why.
Well, at a certain height, it'll become saturated
Why does the air become saturated?
because let me think about it for a second. Uh,
See, in my mind, this is about, I think this stuff is really easy once you've defined it correctly in your head. And this is where you're not getting it defined in your head. Okay, so Tom, why do you say it stays the same?
I wasn't certain.
You were just kind of guessing. Okay, guys, if W goes up or down, do you agree that's changing the amount of water vapor in the air? In order to change the amount of water vapor in the air, what two things do you need?
Liquid water.
Condensation or evaporation?
Well, okay, to change it, you're evaporating or condensing, right? And in order to have that, you need liquid water and vapor. Now, do you have vapor in the box? Yes. Isaac, you said how much vapor is in the box?
W.
Do you have liquid water in the box? When I take a box of air, I'm saying there's a cloud in it to start. Where does the cloud form? Everybody, where does the cloud form?
The LCL.
At the LCL. Does everybody know what LCL stands for?
The lifting condensation level.
Okay, do you understand that's where the cloud starts to form? Until the cloud forms, is there a cloud in the box? So if there's no cloud in the box, is there liquid in the box? If there's no liquid, can water vapor be condensing or be evaporating? If water cannot be evaporating or condensing, can W be changing? So what does W do? It stays the same. So Tim, you said, well, eventually the air saturates. You lift the air till it saturates. Why is the air saturating? Use the analogy of the chairs.
You are so I'm thinking about the saturation mixing ratio, which is the amount of water that can be in the air.
So that's the number of what? In
The
the
number- In the analogy, it's the number of seats that are there.
the number of seats. And the number of people is in the analogy is what?
It is the amount of water vapor in the air.
Okay, so how is the air becoming saturated when you lift air?
The seats are being filled then, right?
No. See, that's the whole problem. If you have 10 chairs and you have 6 people sitting in them, and I said fill the theater, your most common thought is put more people in there until they're filled. But there's a better way. That's not the way the atmosphere does it.
Just take
I mean,
away.
it can. What are you doing? You're taking out the empty chairs. Right? That will fill the theater, won't it? Because if you take out 4 empty chairs, you have 6 people sitting in 6 chairs. That's full theater. Talk to me. Sam, how do you guys display this class? Like, what do you see on your screen right now?
I see a grid of people.
Are you seeing all 9 of us here?
Yeah.
Does everybody have it on that, or are you on the, because sometimes people do it. So
I have all
Sam,
9.
what else was on your screen?
I'm going between Word document.
Are you taking notes on this?
Yeah.
Okay. So do you understand what I'm saying? You guys, okay. So I've had a lot of talks. I talk about COVID teaching with thousands of people. You do know how bad it is, right? I mean, it's horrible, especially for people under the age of 25. That's my opinion. So it's horrible. Do you know why it's, I don't know. How is it for you? Are you okay? Do you have a hard time concentrating, focusing?
I mean, the lecture part is definitely different than what I'm used to or what I was used to.
I mean, it sucks. There's no question about it. And I don't necessarily know the answer. All I know is that students do, even the best students, do way less than they should be. If you were in my class taking the same test, you would have done better on this last test. And I think a part of it is just that you don't have that. Look, I think I have COVID. You don't have that that constant feedback. So I need you to tell me what's going on. With only 8 of you here, me is the 9th, right? I need to know what you're thinking about. Does it make sense what I'm talking about in how the air becomes saturated upon lifting?
Makes sense.
Like,
Yeah.
can you say it in your own words to me? And again, I love you guys. I look forward to this class because especially all you folks are cool. You're fun to talk to. You're good students. But I want to make sure that you're doing well. And whatever it takes, I want to do that. But talk to me about what you're thinking. I need that feedback. That's my biggest hatred of online teaching is I don't get the feedback that I need to know you, how you're doing. So does it make sense to you what we're doing here?
I do have one question.
Yeah.
So it made sense in the lecture last night, but now looking at my notes, it doesn't make sense. So when the box is expanding, when it's lifted in the air, why does it become more saturated?
Okay, saturated, first of all, is 100%. It can't be more saturated. It's like unique. It either is one of a kind or it's not one of a kind. It can't be more unique, right? It can only be saturated, which means the theater is full of people. Each chair is filled. It can't be more filled. So when you're lifting air, what is the air becoming? It doesn't become more saturated. What's it becoming?
It's becoming saturated.
It is becoming, but it is more of something.
Liquid.
Like what's going up when I lift the box?
The water vapor's going up with it.
The water, okay. When you say that, Isaac, what do you picture in your head? The water vapor is going up. What does that mean to you?
Well, I see the molecules in the box also moving up with it.
Okay, then let me rephrase my question.
Okay.
When I lift the box, what values are increasing? Right, because when I said going up, I didn't mean physically going up, I meant increasing. So let's think about that. And there's a lot of answers. Everybody should participate in this. What values increase when I lift the box?
Density.
Is it becoming more dense? Are you sure? Well, you might be sure, but
Today's not my day.
what's the box doing?
Expanding.
It's getting larger, right? So the volume's going up. What's density defined as?
Mass times volume.
Not mass times,
Over volume.
mass divided by volume. So what stays the same? Mass. Why does mass stay the same? What kind of a box is it?
Biggest box.
Right? And what's in the box stays in the box. The number of molecules in the box stay the same. So the mass stays the same of this box. But it's getting bigger, so what does that do to the density?
Causes the density to decrease.
So the density is decreasing. So I asked you what values are increasing when I lift the box. The first one is the volume is. Okay. What else increases? Well, let's do this. What does temperature do? It goes down, right? What does the pressure do?
Goes down.
Goes down. What does the mixing ratio do? It stays the same. Is there anything else you can think of that increases as you go higher? See, Isaac, you said it becomes more saturated. That's just the wrong word. What is increasing is the relative humidity.
Yeah.
It's becoming more humid the higher up you go.
Okay.
What about supersaturated? Why do we use that term?
Okay, so Sam, if you know about this term called supersaturated, which is obviously, something that we're going to deal with, we are not going to deal with supersaturation with parcel theory.
Okay.
And that supersaturation is a weird thing that happens, and we're going to talk about it, but not for a while. Okay, so you don't have to worry about that. 100% is the most you're going to get. So what I'm saying is this. I guess I can do it this way. So the relative humidity is equal to this over this, right? So this is staying the same. What's this
Sharing
doing?
your screen.
Oh, you want me to share my screen? There. You see it up here? This stays the same. This, what's W sub S doing?
Decreasing.
So what is the relative humidity doing?
Increasing.
Inversely proportionally. A equals B over C. So again, that's the easiest equation in the class. That's the one we used 1,000 times. A equals B over C. So when I lift the box, the things that are increasing, the values, is volume and relative humidity. Now, relative humidity, and I'm just going to do it simply like this, just to make it simple. What's the relative humidity
So
based on this diagram?
75%.
Okay. When I remove the capacity, right, the original thing was 3 over 4, which is 0.75. And now what is it?
100%.
100%.
So why did the air get saturated? Because the capacity was going down. Right? Now, I suspect that there's something that you don't understand about this set of equations. What is giving you a problem? What do you think? I mean, can anybody see what you think might be the issue that you don't fully understand?
Why the capacity is going down?
I would think that would be what it is. Why is the capacity going down? And I would also suspect that maybe you go, I don't even know what you mean by capacity. What does that mean? So let's start with that question, Tom or anybody else. What does W sub S, the capacity, mean? Explain it to me.
I would see it as the maximum amount of water vapor that there could possibly be? Or the holding amount?
Yeah, I mean, right, when we deal with the theater, do you understand the capacity? Is the capacity really the amount of people that could fit into the theater? Really? No, it's the number of chairs, right? So does that mean that I can't put any more vapor into the air?
No.
I mean, I could, right? But what does it mean to be at capacity? Do you understand that if I'm at capacity, then what state is the air in? What kind of a state?
Is it
Saturated.
liquid?
Well, the air is not liquid per se. Zach, were you saying something? Or?
Is it saturated?
Well, saturation means what?
Uh,
You're in a what? 2 words. DE.
Dynamic equilibrium?
You're in a dynamic equilibrium. What does that mean? Did I discuss this in the lecture? The dynamic equilibrium? I don't think I did, right?
Don't think so.
Do you understand what dynamic equilibrium of water vapor at saturation would mean? What do you think? I mean, you just tell me what you're thinking. Say something to us. You'd be wrong. I don't care. What do you think that means?
Does it mean that the amount of condensation and evaporation are the same?
How do you guys view Lena's comment?
You agree? Aaron agrees.
Okay, I think that's a good description. So if I have, listen to what you said, the rates of evaporation and condensation are the same, which means what must be present in some container?
Liquid, water, and water vapor.
So imagine that I've got a bunch of liquid sitting in a box that looks like this. And imagine that there's nothing there. It's in a vacuum, which we could have in a vacuum. What are the molecules in the water doing? They're moving around. What will some of those molecules want to do? Do you agree that they're going to want to start coming out of the liquid and becoming vapor? Right? They're moving around randomly. Some of them are going to escape from liquid into vapor, each molecule. Do you now see that there is going to be some amount of vapor that goes into the air? So when this happens, W is increasing. Does that make sense? By the way, if I said that W is a mass, do you agree that's weight? What can that be equivalent to? Or at least almost equivalent to what? What's E stand for? I don't know what chapter this is in the book, but I know we talk about it. Aaron, do you know what E stands for?
E,
It might also be in my notes.
Yeah.
I think there's E in there.
equilibrium. She
Not
says,
equilibrium.
she says equilibrium.
Not equilibrium. W, mixing ratio, which is a mass, grams, is almost equivalent to what?
It's okay, Aaron. Aaron, it's okay. You know, E, B, A, evaporation. Is that what you say? She says evaporation.
Nope. E is an abbreviation for something we call Look, if I asked you what's our working definition of air pressure, what do you say? It's the weight, right? Force is weight over area is pressure. So now I've got W, which is weight, mass, but it's over the water and it has mass. So that's almost the same thing as vapor pressure. It's a little bit different. We're not going to worry about the difference there. But there's some things in this unit that you're going to need to deal with vapor pressure. It's exerting a pressure onto the water. Now, as this goes on, more and more water vapor or water starts to evaporate. But as these molecules are flying around, what do these molecules start to do? Some of them are going to fly and hit the water. Right? Because if they're moving around randomly, what's to stop? If a molecule just goes and moves and hits the liquid water, won't it become part of the liquid water? So there's going to be when you put vapor in the air, there's always this back and forth of vapor turning into liquid and liquid turning into vapor. And at some point, you have so much vapor, more and more vapor goes in there, that the rates of evaporation and condensation are now balanced. That for every molecule that goes out into the vapor, some of the vapor molecules go into the liquid. We're at a dynamic equilibrium, which means that the air is now saturated. Does that make sense to you? I mean, do you picture what's going on exactly in this? Does that make sense? Okay, now, when you have this dynamic equilibrium, do you see that you have as much water vapor as you can possibly have? Can I put any more water vapor in there? No, because if I tried to put more water vapor in there, it would start to condense out. So I'm limited to how much vapor I can put into this system. Well, the amount of vapor that is there when the air is saturated is called W sub S, the saturation mixing ratio. Do you also understand that if there's a saturation mixing ratio, there's probably a saturation vapor pressure? I mean, if mass becomes pressure, then the amount of mass that could be there could be expressed in pressures as well. Okay? So whenever you see these two things, you're almost looking at the same thing. But this unit is in grams per kilogram. And this guy is in what? Millibars. Or pascals, or hectopascals, whatever, millibars. It's a pressure. Does that make sense to you? Now, the question is, well, hold on. Is there any way to put more vapor into the box? Do you understand that when a molecule has a lot of energy, it's moving faster, it's going to go out of the box. It's going to go out of water into the air. And when a molecule has slow energies, it'll go back into water. So what if I made everything hotter? What if I made the molecules move faster? Wouldn't that increase the rates of evaporation by making it warmer? Molecules would be less likely to want to hit the water because they're like, ooh, I'm energetic, I'm gonna stay out here. Now, more molecules will go into the air, but the more molecules I go into the air, eventually what's going to happen is I'm going to start to have more condensation. Until when? Until I set up a new dynamic equilibrium. In other words, how much vapor is actually in the air is more now when it's saturated than it was earlier when it was saturated. What changed?
T. Raise your hand.
right? Aaron said T.
Temperature.
The capacity is a function of temperature. Now, this is a mathematical way of saying whenever you see is a function of, you could say depends on. It depends on temperature. If the temperature goes higher, what does the capacity do? Everybody? Isaac?
I'm sorry, can you repeat the question?
Hold on. What was the question that I asked? I forgot. I'm not paying attention to myself.
When the temperature goes up, what happens to the saturation level or something like that?
The saturation vapor pressure, which is capacity.
Doesn't it increase?
It would go up. So if the temperature goes up, what does capacity do? It goes up. So what's the relationship between those two?
Directly proportionate.
They're directly proportional. Now, again, going to English, we've done present imperfect. This is now subjunctive tense. By the way, I forget who I was talking. I was talking to a literature major, and we were talking about the stuff that I was teaching you guys with present imperfect. And it's amazing how little people do know about tense. And when I was talking to those people, do you know where I learned most of my English grammar? I learned it when I was taking Spanish, because they would use these different forms of the word, and I'd be like, present imperfect, estoy hablamos. No, estoy hablaba? I think that's what it was. Anybody speak Spanish in here? No. Anybody speak?
I took
You took-
classes of it.
But it was amazing. I learned more about English by taking Spanish than I learned about English taking English, which is kind of a sad comment, in my opinion. Okay, so subjunctive tense, do you know what that is? If I was hurting you, I'm sorry. Is that the way I say it? Or do I say, if I were hurting you, I'm sorry? If I was hurting you, I'm sorry. If I were hurting you, which one's right? I was hurting you or I were hurting you?
I'd say
Depends on how you're using it.
So the idea is like, I was hurting you. That's a hurting, makes it imperfect. I was hurting you. I am hurting you. Present imperfect, am hurting. Past imperfect, was hurting. If I was, but when I put the word if, I'm going to make it subjunctive. So I would say, if I were hurting you. There's a musical called Fiddler on the Roof. Do you guys know that musical? If I were a rich man, meaning I'm not a rich man. If I were, then I would do this. Okay, so this is subjunctive, means if statements. Okay, so the point is, if a theater were full, what does that mean? What does that mean if the theater were full?
all the seats are filled.
Okay, that's one way to look at it. All the seats are filled. How would you know how many people could sit in the theater if I can't count the number of seats? Think about that question. How could I determine the capacity, or if a theater were full, if I cannot count the number of seats? Anybody have an idea?
You have to compare the saturated vapor pressure to vapor pressure itself.
Right? So what I could say is, I'm going to let the people come into my theater and I'm going to count them. And once, let's say I count 100, and now I look and there's no empty seats. What I'm saying is that the theater will be full if there were 100 people sitting in 100 seats. And since it's full with 100 people, I know the capacity is 100. I counted the people, not the chairs. So in this example with the box that you have here, the air is saturated when the amount of water vapor, which I can measure, is equal to as much as it can be given that temperature. Does that make sense, Steve? Meaning, I can't put any, I have a certain amount of people. W sub S is what W would be if the air were saturated. That's the way you would define it. W sub S is what W would be if the air were saturated. Subjunctive tense. Does that make sense? So if I made the temperature warmer, do you understand that there could be more water vapor in the air before the air reaches saturation? So now that I have more W, W sub S must go up. Now, draw a graph relating W sub S and T. Now you're going to have to draw that someplace. Show me what your graph looks like then. What's the first thing you do when you draw a graph?
Identify your axes.
Okay, so the horizontal, the abscissa, what would you call that? Which one, what variable do you normally put on there?
The independent, right?
That would be the independent variable. So which two variables are we dealing with?
Temperature and W sub S.
So which one's the dependent, which one's the independent variable?
Would-
Temperature, right?
Does the temperature depend upon W sub S, or does W sub S depend upon temperature?
W sub S depends on temperature.
Okay, so temperature goes on this axis.
Yeah.
And then the ordinate would be W sub S. Show me with your arm what the graph would look like then. Okay, so let me draw it. Okay. Anybody have a question on any of this stuff so far? So let me draw. Here's axis 1. Here's axis 2. I'm going to draw W sub S. And I'm going to say, all right, this is temperature, and this is W sub S. Right? Do you agree with this? Let's see what this means. Let's see what this means. What is a graph really? What is a graph really? And I've asked you this question before, and damn it, you're going to know it by the end of my classes. You're going to know how to interpret and understand graphs. What is a graph really? Come on, Tom, mathematical man.
A collection of ordered pairs.
A collection of ordered pairs. I will accept that as an answer. So do you agree that I am looking at, I'm looking at a set of points, which really, what are the points? They're ordered pairs. So I'm going to put a point there, and I'm put a point there. And then I'm going to put a point there. And I'll put a point there. Okay. And I'm going to say that these points are correspondence. Actually, let me go to arrows. These are correspondence. Do you agree with those comments? Now the arrowhead's going to get larger, and I can't do that, fix that readily. Okay. Now I'm going to do this in red, and I'm going to say, what does this point, since it's an ordered pair, that is some temperature red T. And at red T, there is a corresponding red W sub S. Do you agree? Let me say that to you again so that you all know what I'm saying. This point is at some temperature, independent variable, there is a corresponding capacity red W sub S. Okay, so what's this point? At this point, there is a temperature what? Red T. And what does that correspond to?
W sub S.
A red capacity. And what is the capacity? W sub S. Do you understand I'm saying sub for subscript S? Okay. Does that make sense? Now, are these the same temperature? If they're not the same, they're what? Sam?
Different.
How different are they?
That I don't know.
Sure you do. How different are these?
Say not too different.
Are they the same?
No.
What's not the same? The red T's. So they're different. How do you express different red T? How different are they? Delta T, red delta T. Are these the same corresponding W sub S's? So if they're not the same, they're what?
Delta W sub S.
But in words, they're red delta W sub S. So what I'm saying is, if the temperature increases by some amount, red delta T, what will the capacity do? It will increase by some amount, red W sub S, delta W sub S. Say that. Repeat, write that, actually go write it down. Exactly what I said.
Could you repeat what you said?
Nope. What did I say? You tell me, Lena. Look and tell me what you see.
Well, no, I was writing down that the change in W sub S would be delta W sub S, just like how the change in temperature is delta T.
Isn't this funny? Now, do you understand why teaching is such an interesting thing? I say something, it's really important, and I say, write that down. And do you realize almost all of you always say what to me? Wait, what did you say? I just want you to think about what I mean by that, right? Isaac, you've done that a couple times, right? Like, wait, what did you say? Can you repeat that? Were you listening? Yeah, kinda. But you weren't really putting it down. Now, how many times do you have a teacher that lectures and they talk and you really don't know what they're saying? In my opinion, if the students don't know what the teacher's saying, why is the teacher talking? Listen to me and look at the screen. When the temperature increases by some amount, red delta T, there will be a corresponding increase in the capacity, red delta W sub S. Did you figure out what I just said now?
I got the first part.
What did you write, Sam?
When temperature increases by some amount, red delta T.
Right, okay, so do you see that on the graph? Do you see how that's corresponding to a picture? Then what happens over here on the left side? It's okay. I'm just trying to teach you how to learn. That's all this is all about. I am so tired of a stupid world who can't think their way out of a paper bag. The last thing I want to do is let my students not know how to think. Look what you're doing. You're going on the graph. You're going like this. You're increasing the temperature by some amount. What's that amount here?
Delta T.
Well, what color?
Red delta T.
Okay, and do you understand that corresponds to something going on over here?
Yes.
How much is that?
Some amount, red delta W sub S.
And if the temperature goes up, what does W sub S do?
Increase.
Because they're directly proportional. So for an increase in temperature by some amount, red delta T, there's an increase in the capacity by some amount, red delta W sub S. Does that make sense to you now? Okay, so I want you to do the exact same thing, except this time I want you to use blue. So what does that represent? What is that pointing to?
Blue T.
When I say some blue T, do you understand that's an arbitrary value? Some blue T, and what is that? And then what's the word that you speak next?
Has a corresponding capacity of blue W sub S.
And if I go to this point, same thing. I have some temperature, blue T, corresponds to some capacity, blue W sub S. Are these the same T? If they're not the same, they're
Different.
by how much?
Delta T, delta blue T.
And that corresponds to?
The change in capacity of delta blue S, WS.
Right? Now, let's do this. If here, move this closer to me so I can. What's the next statement? If red delta T equals blue delta T, in other words, red delta T and blue delta T are the same, then what else can you conclude?
red delta W sub S equals blue delta W sub S.
Okay. Does that make sense to everybody?
Yes.
Okay, that means, again, do you at least see how simple I'm trying to make everything? How found just simple things. This is this is that, and then you put it together. Okay, here's the question: is red delta W sub S? I'm sorry, I lied. Is red delta T and blue delta T the same?
Yes.
I would say the answer is yes and no. This, watch this, guys. See, this red and blue are the same. But are they at the same place? So what's the difference between blue delta T and red delta T? Where is blue delta T compared to red delta T?
Isn't blue delta T at a greater value? So they're at different value places, but
Okay,
they still have the same
so,
change.
So Lena, let's say that again. Everybody listen to Lena.
So they're at different value places. So blue T is a greater value than red T, but the delta T with
Well, okay, so can you make it better? You said value places.
So blue T would be at a greater temperature.
Right. And what's a better way to say that? You wouldn't say blue T or blue delta T is at a greater temperature. You'd say a greater temperature. What's it like outside? Well, today's a greater temperature than yesterday. What would you say?
It's warmer.
Right. So do you agree that going to the right on that chart is warmer and going to the left is colder? So there's a change in temperature, but blue delta T is taking place at a warmer temperature. That there's a change in temperature, but blue delta T is happening at a warmer temperature than red delta T. But the numbers are the same. And so the answer is something like this, is you say, well, this might be, delta T might be 5 degrees Celsius, which means blue delta T is at 5 degrees Celsius. But this could be, 20, and this would be 25, and this would be 40, and this would be 45. Does that make sense? They're both 5 degrees apart, but the actual starting value is different. Does everybody understand this term? Unfortunately, this is all wrong. I mean, I shouldn't say everything's wrong, but your graph is wrong. Because what assumption did you make about the relationship between capacity and temperature?
It was linear.
It was linear. You formed it a line. Now, does this line show me that it's directly proportional? The warmer, the greater the capacity. Yes, but that's not the way it is. What it needs to be is, and when a line looks like this, what do we say it is?
Exponential.
Exponential. So what you need to do now is I want you to redraw this picture exactly like this, but with the graph in light blue showing an exponential relationship. So take the time to draw that correctly, independently, and then what I need you to do, pay attention here, I need you to write this first statement, but does that change this answer? So the first statement is the if this, then what? So go ahead and you independently do it and talk it out loud. So you can put your mute on because you're going to individually do this. Draw the diagram talk about this temperature, red T corresponds to a capacity, red W sub S. Because in doing it, you're going to say it another 4 times, and you're going to really solidify this into your head. So do that. How's it coming? So I need to draw the line. And I still need to label the axes. And this time I'll do a red point, and a blue point, and a blue point. And I had yellow arrows. Nope. Shoot. No, I guess I got to do it. Oh. Ah, making everything disappear. Something like that. You know, there's kind of joy to making fun pictures, right? This is some temperature T, the difference of red delta T, and that corresponds to red delta W sub S at some W sub S, W sub S. And then over here, there was blue T, and that corresponded to blue W sub S's. This is not the same T, so it's a delta T. This is not the same W sub S, so it's a delta W sub S. And then I said, you need to rewrite if equals, I'll put the comma, then period. And I go red delta T. And I did blue delta T. And what do I write in between them? If this, watch, if this and this are the same, and that's why I had to redraw it, because I want this to be the same delta T. Does the corresponding W sub S's, are they the same? I mean, this blue delta W sub S looks a lot bigger than the red delta W sub S. So I write that.
That's what we.
Does that make sense?
Make sense? Yes.
Aaron, you're good. How about the rest of you guys? Are red delta T and blue delta T the same?
Yes.
The difference is the same. Blue is taking place at a higher temperature. So listen to what I'm saying. If the temperature increases by some amount, the corresponding change in the capacity will increase by a greater amount when the change takes place at a warmer temperature.
Yeah, that explained everything.
Your look did?
Yep. I just,
Okay.
that was the look of I have to go back and get
Somebody,
that.
well, see, somebody else, tell me what I just said in your own words. Did you understand it? Okay, I tell you what, I'm going to say it one more time. I don't want you to write, because I think this is a student problem. The teacher starts talking and the students are thinking they're dictation machines. When you're writing, are you listening at the same time? Okay, so listen to me. If I don't give you the time to write it down, what do you say to me?
Slow down.
Right? That's what you would say. If I'm not giving you the time to write it, you say, well, hold on, wait a second, I gotta write that down. So listen to me, I'm gonna say it. Look and listen and think. For a given delta T, the corresponding change in capacity will be greater when the change of temperature takes place at a warmer temperature. Now write it down. Were you able to do it, Mina?
No.
What did you write down?
I got at a given change in delta T, and then,
No, not at a given change in delta T. That would be delta T.
oh yeah,
At a given delta T, for a given delta T, there is what? For a given change in temperature, there's a what, Aaron?
Corresponding delta WS.
Corresponding delta W sub S. And how would you say delta W sub S? You could also say a change in
water vapor capacity.
Sure, you could say that, right? And when does the capacity, is it always the same amount for a given delta T? No, the delta W sub S gets larger when the delta T's take place where?
At a warmer temperature.
At a warmer temperature, further to the right. That's what exponential growth is. Now, scale of 1 to 5, what's your understanding of this? 3 4s, 4s.
4.
What do you guys need to get even better? I like to see the fact that I'm getting 4s and up usually. What do you need to make it feel better? Because in my opinion, if I didn't understand something, I would have to say, well, wait a second, I don't understand what this is. That's how I would do it.
It would help Aaron if there were actual numbers.
Well, the same thing it was before, Aaron, right? We could do something like this. I mean, this is 20 to 25 degrees Fahrenheit. So what's delta T? 5. And then this could be 50 and 55. And then what's that going to be? What's delta T? It's still 5 degrees Fahrenheit, right? There's delta T is, but do you understand that the blue is taking place at warmer temperatures from 50 to 55 rather than 20 to 25?
Right.
Now the capacity, and you don't have this information, but if you, and actually you do that in the book where they give you E sub S, because capacity could be E sub S, just like it's W sub S. And over here, you could say, well, this is like 2 grams per kilogram. And this is 3 grams per kilogram. And this could be 6 grams per kilogram. And this would be 9 grams per kilogram. So I'm saying when the temperature raises from 50 to 55, the capacity goes up by 3 grams per kilogram. Here, it goes up by only 1 gram per kilogram. Now, don't quote me on those values, but does that help?
Yes.
Okay, well then, that was a question worth asking. How are the rest of you? Okay, now, what question as a human being, as a child of education, if you were in 8th grade, what do you think, what do little kids ask all the time?
Why?
Why? Even be more like bratty sounding. Why? Couldn't you go, so what? So who cares? Why does this matter? Isn't that what kids do all the time? Why does this matter? When you get older, do you stop thinking this way? No, you just stop saying that out loud because you're trying to be somewhat of a respectable adult, I think. But don't you feel that way? So why does this matter? Why are you spending so much time caring about this? That's a legitimate question. Do you know what the answer for that might be? Oh, welcome back, Ryan.
Sorry, my internet was
That's
messing.
okay. Do you know what the answer to that question do you think it is? Tell you what. The other day, I'm going to move you guys back over here. The other day, I wrote this down. How much is the wet adiabatic lapse rate?
+6.
Okay, no, absolutely not. Do not ever say 6 degrees Celsius per kilometer in my class, ever. Does the book say that?
Yeah.
Yeah, I hate the book. Actually, I don't hate the book, but don't ever say that. The wet adiabatic lapse rate is actually the dry adiabatic lapse rate minus the amount of latent heat that is being released, right? Because eventually what happens is I lift this box, I lift it up, it expands, and it eventually becomes saturated. If the box becomes saturated, where am I? I'm at the LCL, right? And how did the box become saturated? It had some W, which is constant. It had a capacity, but because the temperature is getting colder, do you agree that the capacity is decreasing? So that means, what does the relative humidity do? Right, we did this. Eventually, at the LCL, the air is saturated. So what's the relative humidity at the LCL? 100%. And if it's 100%, then what can you tell me about these two values?
They're equal.
Right? How much there is how much there can be. I'm in a dynamic equilibrium now. I need further. Now, I continue to lift the box. The pressure continues to go down. The box continues to expand, and it continues to want to cool at 10 degrees Celsius per kilometer. But if it's cooling, watch this. You ready? If it's cooling, what's the capacity doing?
Decreasing.
It's going down. Why is the capacity going down? Because the temperature is going down. And what's the relationship between temperature and capacity? They're directly proportional. It's getting colder, the capacity goes down. But can the bottom number be less than the top number? So what does the W have to do? Also, it has to go down by the same amount as the bottom number. Because once you're in a cloud, what's the relative humidity in the cloud always?
100%.
100%. So how does W decrease? How do you decrease the mixing ratio? Everybody speak your answer. Unmuted. On the count of 3, I want you to give me the answer. I want you to say something. I don't care how wrong it is. How does W go down? 1, 2, 3.
Condensation.
Take out water vapor.
Lower temperature.
Patient?
No, Sam. That may be happening, but that's not what it is. W goes down by taking vapor out of the air. But what do you call taking vapor out of the air? You said it before.
Condensation.
Condensation. So do you agree that W goes down by condensation? So in the cloud, you start making the cloud because water vapor condenses. But what do you say when I say water vapor condenses?
Latent heat is released.
Oops. Latent heat is released. And when you're releasing latent heat as you're cooling, what does that do to the rate of cooling? Listen to me, listen to the question. As latent heat is being released as the air is cooling, what does that do to the rate of cooling?
It decreases it.
Decreases, it slows it down, right? So why is there a minus sign here?
Because heat is released and that kind of warms it up, but it
Right? And elapse rate's a rate of,
cooling.
so we say positive numbers mean it's trying to get colder. Latent heat is trying to make it hotter. So what is the wet adiabatic lapse rate? I don't know. It's less than the dry. How much less? Depends. What does it depend upon? The amount of latent heat that is released. Well, what determines the amount of latent heat that is being released?
The condensation of the vapor.
How much vapor condenses, right? So in this equation in yellow, you have to say, well, how much, what is, hold on. Let me do it this way. You have to say, what does that depend upon? That's what that little arrow means. Depends upon. How much water vapor condenses. Now I could write that down, how much water vapor condenses. But how much water vapor does condense? How do I write that down? Okay, stop for a sec. Oops. How you doing? Zach, how you doing?
Pretty well, I guess.
I'm not doing well.
Why, Tim?
Did you hear the news about Tiger Woods?
No, what happened?
He got into a car accident, rolled over. He's in the hospital right now.
Are you serious?
Like his legs and his body's in like severe to critical condition. He's in surgery.
God, are you kidding me? Are you a golfer?
Yeah.
Wow.
Well, I'm just a fan too.
Yeah, a fan of Tiger Woods. He's been amazing. One of the greats. That's really sad. I'm sorry to hear that. You know who my favorite golfer was? Payne
Oh, they had
Stewart.
to use the jaws of life.
Did they really? Wow. My favorite golfer was Payne Stewart. That's even more tragic. You guys know who Payne Stewart was? He's a guy who used to wear these like plaid pants, the knickers, and he'd have the big socks pulled up and he had a little Irish cap that he would always wear. He was in an airplane, and I'm at home watching the news at lunch, and they go, Payne Stewart's airplane's not responding. And they were flying in a private Lear jet, and then they sent F-15s after them, and they're looking in the airplane, and they don't see any movement. So what had happened is there was a leak, and they all died of hypoxia. So and basically hypoxia means you don't have enough oxygen because you're up so high. You just kind of, you get tired and you don't realize what's going on. The next thing you know, you pass out and your body stops working. So the plane kept going up. It flew. It was over South Dakota. It ran out of gas and it crashed straight in the ground. And they were going to shoot it in case it was going to land in someplace. They were going to shoot it first, but it was in the middle of an open field. And it just crashed, and that's the end of Payne Stewart. So I'm sitting there at lunch watching this happen live, and I'm going, that was my favorite golfer. So I know
Tiger
that.
questionable things, but I don't know.
What'd you say, Jim?
I know Tiger's done like a lot of questionable things, and
Well, human beings are a mixture of good and bad.
yeah,
If you focus on the bad, you're going to erase the entire history of the world. How about we focus on the good of people and try to change the bad? You know, Tiger did a lot of work to try to get his life in shape. I'm not sure. Maybe this is what he needs to do it even better. How are the rest of you doing? Isaac, how you doing? How you doing at school? Class. Oh, hold on a second. Let me do this. Resume recording. I'm singing.
I'm in a store.
My
I'm
dad.
singing.
Name the movie.
Isn't that Elf?
It is Elf. Okay, so back to our guy.
What's a Christmas gram? I want one.
Do you understand what is going on so far with this? We're saying that the rate at which a parcel of air cools when it's saturated is going to be determined by two things. It wants to cool at the dry adiabatic lapse rate, which is 10 degrees Celsius per kilometer. That dry adiabatic lapse rate is a result of the first law of thermodynamics. Heat in equals work plus change in T. Expansion is work. In order to do work, I need energy. Energy comes from within the molecules. All of these are guaranteed, dictated by the nature of air. And that's a fixed rate. But then, at the same time it's cooling, water vapor condenses, latent heat is released, and that heat is being used to slow the rate of cooling of the parcel. Got it? And I'm saying, what determines how much latent heat is released? Give me the answer. Use full sentences. Zach, use your full sentences.
How much latent heat is being released?
Is dependent on.
Is it dependent on the change in temperature?
Not yet. What's releasing heat?
The molecules, like the bonds?
Not the bonds. What is releasing latent heat?
Is it condensing water vapor?
Condensing water vapor. So how much latent heat is released is dependent upon how much water vapor condenses. But how much water vapor condenses? Okay, if I were in class, I would do this for you, but now you're gonna have to pretend. So I've got some coins in my hand. How many coins do I have in my hand? How much money do I have in my hand?
A handful.
Okay. And how much is that? You said this earlier when we were talking about water vapor. How much money do I have in my hand?
W.
Okay, it would be similar to W, right? It's just some amount, right? Now, imagine that I take out some of the coins. How much is still in my hand?
Some amount.
Some amount. Is it the same some amount?
No.
So how much is left depends on what? How much I took out.
Yeah.
How much water vapor is in the air when I start?
Some amount.
Some amount, how much? Oh, you said it, you just said it to me. How much water vapor? Some amount,
W.
right. And then I condense some of it out. How much vapor is still in the air?
W.
Still some amount W. Is it the same
Yeah.
W?
No.
Then it's what? How much came out?
W.
Not W came out.
The W.
Right? I have some amount. Let's say that I have some amount in my hand. Let's say I have 80 cents. and I take some amount out, and I have 60 cents now in my hand. How much did I take out? 20 cents. 80 minus 60. The difference is 20. That's how much came out. So I have some vapor in the air. How much, everybody? Some amount, W. Some of that condenses. Now how much is left in the air? Some amount, W. Is it the same amount? No. If it's not the same, it's different. Delta W. What determines this? What determines the change in W?
Initial W and the ending W.
That is how I determine that. But what's causing it to change? Why does water vapor condense in the first place?
It's delta T.
No. Why does water vapor condense? Here. You guys, watch this. I'll do this once really quickly.
Is it because it canned it?
What's my relative humidity?
Percent.
60%, right? I've got, what's my W?
6.
What's my capacity, W sub S?
10.
Okay, so when I lift the air, what starts happening? I start removing chairs. Now what's my relative humidity?
75%.
75%, 6 out of 8, 3/4. Okay, now 6 out of 7. Now what's my relative humidity?
100%.
100%. I have 6 sitting in 6, right? And then the question is, when I continue to lift the air, what happens? The temperature gets colder. When the temperature gets colder, what do I take out?
You lose the seats.
I lose a seat. But before, what kind of seats did I take out?
Empty.
Now, what do I have to do? I'm taking out a full seat. So what does this person have to do? Go away. The people going away is water vapor condensing. So listen to the question. Why does a person have to leave? Why does a person have to leave my theater? When I do this,
There's no more room.
there's no more room. Why do they leave? Because they have to. I don't have the room. So why does water vapor condense?
Because it has to.
That's the answer. Why does water vapor condense when the air becomes saturated? Because it has to. Any additional cooling is going to cause what to change? The capacity goes down. So why does water vapor condense? Because the capacity is going down. I've run out of empty chairs. I have to get rid of full chairs. So what determines the change in W? The change in W sub S. Do you agree that if I took out 1 chair, 1 person leaves? If I take out 4 chairs, 4 people leaves. The number of people leaving is determined by the number of chairs I remove. So the amount of vapor that condenses, delta W, is determined by the number of, or the loss in the capacity, delta W sub S. Does that make sense? Are you following the reasoning and the logic to this thing? Okay. What does this depend upon?
Temperature, right? Change in the temperature.
Well, which one is it?
The change in the temperature.
How many people say it's the change in temperature? How many people says it's the temperature? Tom, what do you say?
Change in temperature.
Is that it?
Well, yeah,
Look on the graph you drew. Does the delta T determine delta W sub S? Yes, but not alone. What else affects it? Does the same delta T create the same change in capacity? It's also,
okay.
in other words, the change in the capacity is determined by how much the temperature change or how much the temperature changes and the temperature where that change takes place.
Yeah, because it could be like a lesser change.
Right. So if I said, hey, the temperature goes down by 5 degrees, would you agree that the capacity is going to change by some amount? If it went down by 10 degrees, do you agree that the capacity would change by more? The bigger the delta T, the bigger the W sub S. But for a given delta T, 5 degrees, at warmer temperatures, the capacity changes by more. So the amount, the value of this is determined not just by that, but also by the temperature where that change takes place. The warmer the temperature, when the air is saturated, the greater the capacity changes.
I have a question.
Yeah.
How come we don't talk about like height in this?
Okay, so basically what I'm saying is, if I take a parcel from here to here, it's cooling at some rate, change in temperature with respect to height. But there's going to be a given amount of temperature change over that distance. And I don't care about that distance. I know it's cooling at a rate. So I'm more concerned about the delta T, not the delta T over delta Z, which we could still do.
Okay.
So what I'm saying here, and I think the question is legit, is that when I say is dependent upon, this little blue arrow depends upon, what I'm really saying is it's not exactly this, it depends on it. The more of this, the more of that.
Well, I was just thinking because if like the change in temperature at a lower height is going to be not as severe because it's like, let's say we go from 10 degrees to 5 degrees. So if there's 5-degree temperature change, the change in W sub S is going to be less as well compared to if we're at, 2 kilometers in the sky and we're in the negatives.
Well, no, well, hold your thought,
Okay.
because I'm going to show you a way to see this better. Okay, so hold your thought. It's not really a function of the height change as much as thinking of it in terms of a slope, which is a rate. But we'll go to that in a second. So what I'm saying is, now listen closely. Do not write this, just pay attention, okay? The wet adiabatic lapse rate, the rate at which a parcel of air that is saturated and creating a cloud, the rate at which it cools, it's trying to cool at 10 degrees Celsius per kilometer because it's expanding. But at the same time it's getting colder, it's also being warmed by the release of heat that's hidden within it. The amount of heat that's in it depends upon how much water vapor is condensing. The more vapor that condenses, the more heat. What determines the amount of vapor that condenses is the change in the capacity. The greater the change in the capacity, the greater the amount of condensation. The amount of capacity change is determined by the temperature change and the temperature where that change is taking place. In other words, at warmer temperatures, watch, at warmer temperatures, for a given drop in temperature, that is going to cause this to be more. The capacity will change by more because it's exponential. If the capacity is changing by more, then this changes by more. But if this changes by more, this becomes what? More latent heat. What does this become? Which way? If this is bigger, this is bigger. 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 If this is bigger, what's this?
Forward. Less.
Bigger.
Less. Less, because I'm taking it away. It's a minus. The bigger this is, the slower the rate of cooling of the parcel. But what's instability? A race to get cold between the parcel and the environment that we want the environment to win. The environment can only cool so fast. What we want to do is get the parcel to cool slowly. What makes this a smaller number is for all of these things to be bigger. In other words, we want the air to be saturated at high temperatures. When the air is saturated at high temperatures, we're going to be able to get out a lot more latent heat. Why? Because the relationship between temperature and capacity is the ultimate thing, is exponential. The warmer it is, we're getting a lot more vapor by lots. We want condensation to take place when the temperature is really warm, not when the temperature is really cold. This is where we start condensing a lot of latent heat. And we're using that latent heat to make the cloud warmer than the air around it. Now, I'm not going to say that again because it's on the recording. You go back and get it. Scale of 1 to 5. Give me your idea of where you are at. I'm getting a lot of 4s. You guys are self-evaluating that you're 4s. Aaron, what are you at?
She thinks 4.
Okay. Do you think this is easy?
Is it easy?
I mean, here, I want you to understand something, guys, because this drives me crazy in human beings. Do you think this is easy? Wouldn't you think this is fairly complex? I mean, there's some serious information here. We're thinking at a high level. Does this seem like it's high school to you?
No.
You're doing college level science, physical science, hard crap. And you're telling me you have about an 80% understanding of it? I don't want to hear people who go, well, I can't do math or science, because that's bullshit. You can do it if you learn how to think. It may take you longer. There's some people who are really smart, and I've known those people. They're really smart and they get it really fast. But even the really smart people have to learn it. They may learn it at a faster rate than you do, but it doesn't mean that you can't do it. So when you're going through life, just make sure you get that, folks. You have the ability to learn. You just have to learn how to learn. And then cut yourself some slack and do your best. Does this make some sense? Do you have any questions for me about this?
Can I have you clarify one point?
Uh-huh.
So what I understood was that you said when the air is saturated at high temperatures, there's a lot more latent heat being released. Is that correct?
Well, Yes, look, like if we look over here, Lena,
Mm-hmm.
let's say that we're saturated at that temperature. Okay, which means W and W sub S are the same. So when I cool the air by a little bit, right, there's the cooling of the air this way, delta T. Look at the capacity change, which means you're condensing out a lot of water vapor, which means you're releasing a lot of latent heat, and you're really going slow on that rate of cooling.
Okay.
If I were to go from here to here, for that same temperature change, I'm only going down by a little bit of capacity, which means I don't release as much heat, which means this is a bigger number.
Okay.
So look at this inequality over here. This is really true. It's really less than or equal to. When is the wet and dry adiabatic lapse rate equal?
Below the LCL.
Okay, you could say below the LCL, but that's not really the case because below the LCL is the air saturated. Do you know what I'm saying? So it's got to be saturated. I'm only in the cloud enough. But do you understand the higher up in the cloud that I go, it gets colder and colder? The colder and colder it gets, is there any water vapor left to condense? How much when the air is really cold, how much water vapor can be there? Hardly any. If there's hardly any water vapor that can be in the air, as you cool it, how much has to come out? Not very much. So this becomes smaller and smaller, and the wet adiabatic lapse rate becomes bigger and bigger. So let's think about this for a second. And Tim, this is what I wanted to talk about with you. So let's go here. Let's erase this. And we'll say, here's my graph. And this time I'm going to label this graph temperature and height. Now I'm dealing with lapse rates. When I lift a parcel, how does the parcel cool? Dry adiabatically until when?
Till it becomes saturated.
And where is that? At the LCL. Now the parcel cools less. Draw what the wet adiabat would look like. By the way, Kevin, for you and Aaron, did you get my message about sending me the wrong thing?
No, I didn't get that message.
It was in the last assignment. It's like you had 3 attempts at it. And you sent me some sketches of lapse rates and things. I just don't think you sent me the right document.
Okay, I'll double check.
Yeah, so double check on that and then you can resubmit it. So what's the lapse rate do? What's the line going to do?
Becomes steeper.
What does that mean?
I
Well,
mean,
here, let me do it this way. Is it this way more or this way more?
first one.
It's more like this. And so you could say, well, there's the wet adiabat. But if that's the case, what are you telling me this wet adiabatic lapse rate is? Constant. But it's not constant.
Yeah, it's gonna have to be a curve then, right?
It's got to be a curve. Which way will it curve? Will it curve this way? Oh, sorry.
No, the other way.
Will it curve this way? Or will it curve this way? First or second, everybody?
First.
Tim's pretty confident it's the second one. So Ryan, if you did it this way, what is the lapse rate becoming up here? Do you understand that would be bigger? The temperature is like, this would be closer to 0. that there's no temperature change as you go higher. That's the same temperature. That couldn't be right. The colder you get, the slower, or the colder you get. Let me draw it this way. When you're at really cold temperatures, this becomes really small. When this becomes really small, this is closer to being the same. 10. So in other words, the line, is going to become more like this until it eventually becomes the same slope as the dry adiabatic lapse rate. It eventually goes back to being dry adiabatic, cold enough, because there's no more water vapor being condensed. Does that make sense, Ryan? Because the higher up you go, the colder you get, the less water vapor that's going to condense, which means it's going to cool at a faster rate. That's really important. That diagram I gave you with all the red arrows pointing up, and then this becomes less, super important that you get that, you know, the subtleties of that. So whenever I look at this, you have to understand something. That is how parcels always go up. They will always go up dry adiabatically to the LCL and then wet adiabatically after that. They will always look like this. From now on, when I draw a parcel and I plot out its temperature, it's always blue. The environment is always red. And because we're going to do it eventually, the dew point is green. Does the shape of this graph make sense to you? Tim, this is what you were kind of talking about in terms of height.
Yeah.
So what you're saying is that the line goes up like this, right? And then it gets steeper and or it gets more and more this way. Again, I can't use the word steep because you're not putting the independent variable in the right axis. So it becomes more this way. The higher up you go, the greater the lapse rate, because the higher up you go, the colder you're getting. And the colder you're getting, the less water vapor that's condensing.
So,
Less water vapor that's condensing, the less latent heat.
so is it becoming like that because you're producing less latent heat?
Yeah, absolutely. Right? If what makes these two guys different is this, the less this is, the less different they are. Eventually, when there's no more latent heat, then these two are the same. If this becomes 0, then the wet and the dry are the same, which means it looks like a dry adiabatic lapse rate of 10. And the idea is this. That's what exponential is all about, right? So if I look at a graph that's exponential like this with temperature and W sub S, at some point the temperature is 0. Well, when is the temperature 0? Not 0 degrees Celsius, 0 Kelvin, absolute 0. At absolute 0, is there any vapor in the air whatsoever? No. Is there any capacity? No. But this line is so flat for a while before it goes up, you're pretty much barely going to it. It's like doing this, Ryan. So let's say that we cut numbers in half. Okay? So let's go 16. Cut it in half. What do we got? We dropped by 8. right? Cut it in half. What do we get? Now the change is how much? Cut it in half. Now the change is 2. Cut it in half. Now the change is 1. Cut it in half. How much is the change? 0.5, 0.25, 0.125, 0.0625. And so do you see how the change is getting less and less and less and less and less? Exponentially. So when you get down really cold, there's hardly any water vapor coming out of the air. You know how people sometimes have said, oh, is it too cold to snow? And the answer is no, it's not that it's too cold to snow. It's just that when it's really, really cold, how much vapor are you able to take out of the air to precipitate out? And the answer is hardly anything. So when it's really, really cold, you could get some flakes falling, but it's never going to accumulate. But we're dealing with this more in terms of thunderstorms because we want the air to be unstable. So let me watch this. You're still seeing the screen? Let me do this. Here is a map. And I'm looking at what we could, oops. Do you see in here, the red line is the temperature of the environment, and I plotted out the temperature of the environment. The green line is the dew point. So watch this. If I showed you the text, it tells me the temperature and the dew point. Fair enough? But the blue is the temperature of the parcel. And the temperature of the parcel is straight like that until here. And then what does this parcel do now? You see how it curves in this big line? And eventually down here, negative 60 degrees, it's really cold. And can you tell the difference between this dark blue line and the light blue line? They look parallel, don't they? So by the time you get down to negative 50, negative 60, your temperatures are cooling dry adiabatically. Does that make sense to you?
So the colder and higher it's, the more stable it becomes.
Well, yes. Now we're going to have to do some trickiness, because do you agree that the parcel is getting cold pretty fast? So if you said, what's the stability of the atmosphere? I'd say, yes, it's becoming more stable. But we can define stability or instability in two ways. One of them is about the environment, what we call static stability. And one of them is dealing with the parcel. So the first thing I want to do is I want to deal with the parcel. So if you've gotten a 4 on this, what I'm going to show you now is going to be really easy. Okay, so I'm going to exaggerate these lines a little bit. Okay, here's the parcel. Here's the environment. Do you agree that the parcel, when I go to here, is colder than the environment? If I let the parcel go, what would happen to that parcel? It would come back down. Right? Stable, stable. And in the race to get cold, who's winning this race up to this point?
Parcel is.
The parcel is. That's stable. We don't want that. But now I get to the LCO. Now the parcel goes wet adiabatically. And wet adiabatically looks like this. If I lifted the parcel to here, what would the parcel do? It would rise by itself. Do you agree it's warmer than the air around it? Again, the blue is the parcel, the red is the environment. It was stable down here. It's unstable up there. Where did it switch over? Where did that parcel go from being stable to being unstable? Do you agree it's right here where the lines crossed? That's called the LFC. The level, oops, I'll try to spell right, of free convection. Do you agree that to a meteorologist, convection is rising air? And if it's freely convecting, that means it's doing it by itself. That's what freedom is. You can make your own choices. And that's where that starts to happen. This is the level of free convection. Now, let's continue on this thought. Let's just, for the sake of it, say that there's my environment. But do you agree that the parcel is going to start increasing its rate of cooling until it goes back to being dry adiabatic? And at some point, it'll have the same slope as it is down here. So I can go back to a straight line. So do you agree that this slope and that slope are the same? They're both dry adiabatic. If I lifted the parcel to here, what would the parcel do? It'd be colder and start coming back down. Where did it, so here it's stable again. Where did it make the switch? Over here. What's that called, Lena?
That was the, oh my gosh. Oh, the EL.
The EL, which stands for the equilibrium level. So this is where the parcel started to become unstable, and this is where it stopped becoming unstable. So what that tells me is this. I'm going to shade this area in between the parcel and the environment. And that area is known as PBE. PBE stands for positive buoyant energy. There's another name for that, Sam. What is it?
Ape.
CAPE, which stands for convective. No, I can't draw it with this. Available potential energy. So PBE and NBE are exactly the same thing. Positive buoyant energy, convective available potential energy. Okay. What do you think this area represents? Take a wild guess.
Negative buoyant energy.
NBE. negative buoyant energy. There's another area that I would shade in. Where else would I shade that in? That's NBE also. Now there's another name for negative buoyant energy. And it's called SIN, which stands for convective inhibition. Convective inhibition. So NBE and SIN are the same. PBE and CAPE are the same, just different terms. This one says the parcel is going to go up. This one says the parcel is going to go down. And it switches over where they intersect. So a good way to remember things is that the LFC is the start of CAPE. And what's the EL? What would you think?
Of Cape.
Yeah. So you don't want to say it's the start of NBE. This is not the EL. It's the end of CAPE. Pretty easy. I mean, this is way easier, isn't it? Doesn't that make sense? So just so you have some idea, you guys put your pencils down. I don't want you to draw this, but I want you to see something. Look what happened, and we'll talk about this more on Thursday. Look what happens here if I saturate at a warmer temperature and I go up this way. You see I'm going to get a lot more CAPE, which means the amount of CAPE is how unstable the air is. So if you want to know how unstable is the air, the answer is the amount of CAPE. So Tim, you asked, higher up the air is getting more stable. Yes. And then what eventually happens to the environment? Do you agree the environment eventually does what? It goes into the stratosphere and the temperature gets an inversion. So in the race to get cold, what's the environment doing? It's getting warmer. You're going to stop. There'll be no thunderstorms. The thunderstorms don't do anything. So that's where we're going to kind of draw these parallels. So the next thing I want to show you, let's get rid of this. And I'm going to go to our academics. No, I don't want that. I want Blackboard. And on Blackboard, we have more labs. Are you seeing this still? I didn't stop sharing, did I? No. So there's two labs here. There's the water vapor lab and there's the instability lab. And we did some of this and some of this. So what I want you to do for Thursday is, let's think about this. You have a lot of studying to do. The stuff that we went through today, I expect that you know it. I expect that you know the stuff that we did today. So you have studying to do. Make sure you review your notes, put them together, do a really good job. And then I want you to start working on these two labs. And I want you to try to do problems. And you're going to go, oh, I know what the answer to this is. Or I understand what's going on here. And some of them you're going to go, oh, I don't even know what that is. So I want you to answer the questions that you think you know the answer to. And if you go, I don't think I know this, I don't know what to do on this, don't worry about it. But that means I need some of those things answered. Does everybody understand what you're doing? So you don't have to do all of it. It's not due yet. Just come to class Thursday prepared. Any questions on today's stuff? You learned a lot today. You look like you might actually be collegiate level science people.
So do you just want us to look at the water vapor lab, the instability lab?
Yeah, and there's some things in the water vapor lab. In fact, there's a question in there. I'm thinking of you specifically, Isaac. You'll understand. You'll go, oh, that's what I asked in class. So try to answer those. Some of them you're going to know, and some of them you won't. But look at it, and then if you feel like I don't really know what this is, and you can't figure it out, don't try to figure it out. Just
Okay.
we'll go to it a little bit later. And same with the instability. You'll see these concepts in there to kind of help you a little bit. Okay, anything else? And then Thursday, I'll see you. So Sam, stick around. The rest of you guys, any questions?
You know, we had a question about the homework last night,
Okay,
using W or E. So we're confused about that.
okay. Whenever you're using W, you could substitute with E.
Okay,
And like all the graphs, E sub S versus temperature, W sub S versus temperature, same thing.
okay.
All right, and then we'll assign, some of you have already done the geography lab. So I will assign that. If you've already done it, you turn it in, that's great. That's something that you'll be working independently on that. So I'll talk about it on Thursday. But right now, I want you to be done with class, and I hope you have a great